Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 5, Lesson 2, Piecewise Defined Functions. After this lesson, you'll be able to graph and interpret a piecewise function. For the explore and reason, we have this table representing a relay race. We have the 4 different runners. We have the time that they spent running. That's our x value. And we have the total distance of the race that they cover. So this is a 4x1 mile, and they're each running a quarter mile of the total race. So they each run 0.25 of a mile. So first let's graph it and let's see what happens. We can think, does every runner run at exactly the same pace or the same rate? No, they don't. So we should not have a linear graph. We're not running at a constant rate. So let's see how this graph turns out. The first runner, I have the time on the x-axis, so they covered 3 minutes. They ran for 3 minutes and they covered 0.25. So I made the y-axis very, very zoomed in so we could see. There's the first runner. The second runner ran for 5.75, so almost at 6, and they covered the next 25. So there we go. There's runner number 2. Runner number 3 ran for 9 minutes, or 9 minutes into the race, okay, and their distance they covered was the third. Okay, so 9 minutes into the race, there's the third runner, and then the fourth runner took us to 11.5 minutes, and then they got to the end, to the 1 mile. Okay, so if we were to zoom in, we would see that they're not covering the same rate. We would not connect them with the same exact slopes. Trying to see if you could show the difference. So not quite, slightly different. It's not going to be perfectly straight. And we could figure out the rate of each runner. Runner number 3 covered 0.25 in 3 minutes, so their rate is different than someone who covers it in, if we check the distance or the time difference, second runner covered their distance in 2.75. So they covered their lap, if you will, in less time. Okay, and the next one would be 3.25, so they took a little bit longer to cover their distance, right? So they're running at different rates. So we can see there's different sections of our graph. Who is the fastest runner? Looks like the fourth runner, which usually happens. The fourth runner is usually the fastest, but they covered their quarter mile in 2.5 minutes. Example 1, understanding piecewise functions. So we're going to go over some definitions, look at it on a graph, and then how it's notated or how we write piecewise functions. So a piecewise function just means we have more than one piece. Okay, it's not just one continuous linear equation. And we can look at absolute values and the graphs of absolute value functions to learn about piecewise functions, because we can see in an absolute value function we have 2 different sections. We have a section that has a negative slope, the green section, and we have a section that has a positive slope. Now the slope is going to be the same magnitude because it is symmetrical, but one is negative and one is positive. So we can think of these lines, if we imagine they continue down, we can see that we actually have 2 sections of 2 different linear equations, and we can write the equation for each of those lines. And then we need to define the interval or the section of input that each piece represents in the graph. So for the first one, with a negative slope, we know the slope is -2. And so to write that equation, they go through the origin, so there's no y-intercept. So our equation for that green section, the decreasing section, would just be -2x. And it's part of that green line up until we get to 0. So here's our interval. X is less than 0. That will be covered by the green line, or the decreasing section of our absolute value function. But once we get to 0, it changes direction. So now we have a different equation. Instead of having a -2 slope, now our slope is going to be +2. So our equation for that line, for the blue line, would be +2x. It still goes to the origin, so no y-intercept. And it fits that blue line. It will fit that 2x equation when it equals 0 or anything greater. So we've defined that interval. So you can see when we're writing a piecewise function, you'll know it's a piecewise function because you have these brackets, and you'll have a linear equation and an interval for each piece. Okay, that's important. You have the equation for the line and the interval that that line exists. Okay, so if I go back to my graph here, the absolute value function does not exist anywhere here. I know I imagined that line would continue, but for the absolute value function, it does not exist there. It only starts at 0 and then continues on to the right. Same with the decreasing section. It does not exist anywhere here along that line. It only exists where it's less than 0, where my input is less than 0. So we're going to practice drawing a graph of a piecewise function, and we can draw the whole line, but then we can just erase the section that does not exist in the graph. So here we're going to write this equation as a piecewise function. So it is absolute value. Let's remember our transformation rules. It has a negative. So what does the -3 tell us? It's going to be downward facing, right? And it's going to have a slope of 3 and -3. So I'm just going to rough sketch it. There's no change to my vertex. So it's going to start at the origin, and it's going to be, since it has a slope of 3 or -3, it has that scale factor, it's going to be skinnier than the parent function. So it would look something like that, skinnier, downward facing. And let's write the equation. So f of x equals, and then use our brackets to say it has two different equations for the two sections. The first section is increasing. That means it has a positive slope. So the slope would be +3x. Again, it goes through the origin. Now we need to define the interval. So it fits this blue equation. It fits this equation up until it gets to 0. So the interval I will define for my input is when x is less than 0, then it will fit that blue section, the equation 3x. For the next section, it's decreasing, so it is a negative slope. That means it will be -3x. And the interval for that section is everything equal to 0 or greater than 0, because we continue on and on to the right. Everything greater than 0 and equal to 0, it will fit on that green line. Again, I'm not paying attention to anything beyond that section, okay, because that is not included in our graph. Okay, so now we're going to take the equation written in piecewise notation and we're going to evaluate it. Okay, we have to look at the intervals to figure out which equation to use. So if we're evaluating f of 1, that means my input is 1. I have to look at my interval. Where would that be? Is f of 1, is my input of 1 less than or equal to 2? Yes. So it would fit this first equation. So I'm going to plug it into this equation, x plus 1, because my value of x fits this interval. It is less than or equal to 2. F of 2, now my input is 2. Again, it fits this interval where it's less than or equal to 2, so it's also going to fit the x plus 1 equation. So all we do is plug in 1, that's my input, plug it into that equation, 1 plus 1 is 2. Or if my input is 2, 2 plus 1 is 3. For the next input, the input is 3. That fits this interval. It is greater than 2, so we need to evaluate it using this equation. It's a different section of the function. So we plug in our input into that equation, -3/2 times our input, then add 6. And when we do that, we get 3/2. So make sure with piecewise functions you are paying attention to the interval. That will help you decide which equation you use. Now let's look at graphing this function. So same thing, we're going to pay attention to the intervals and then graph the equation. We know how to graph a linear equation. We graph the y-intercept and then the slope. So for the first section, again, that's our green section. I'll call it green, I don't have a red highlighter. The green section, anything less than or equal to 2. So when x is 2, I know I'm going to change direction. Okay, so here's where I change direction, when x equals 2. And I follow that slope and y-intercept. So my y-intercept is 1, and then my slope is 1, so I go up 1 over 1, up 1 over 1, and we can draw that graph. Okay, so here's our first section. Now, again, I'm going to erase a couple things. We could extend this line. X plus 1, the equation for x plus 1 would extend all the way over, okay? But it does not continue on that green line. It stops when x is equal to 2. So it stops right there. That means everything here does not exist for my function. So you could put a closed circle there because you know it can equal 2 and still fit this x plus 1. For the next section, and we have a different equation. So now we're going to graph our y-intercept at 6. So you can see if I extend this line, there's my y-intercept of 6. And then I do my slope down 3, 1, 2, 3 over 2. Down 3 over 2. Okay, down 3 over 2. So we can graph that blue line using this equation, using our slope-intercept equation. But we have to think, what's the interval? This blue line only exists in the function when x is greater than 2. So all of this, so here's 2, anything less than 2 will not exist in my function. So you can erase them. And it only exists starting at 2 and then continuing down that blue line, again, because x is increasing as we go to the right. So it might be helpful to draw the line as you normally do, like it's a linear equation, and then erase or cross out the sections that don't fit that interval. You could also just pick input values that fit the interval. So here you can see they just picked input values that are greater than 2 and graph them. We didn't include 2 because here it's not equal to 2. 2 was included in the first equation, in the green equation. So you can just make sure you're careful on what inputs you choose, or you can graph the whole line and then erase the section that does not include that interval. Try it number 2, graph this function. So we have 2 pieces. Okay, we've got the first piece, x minus 2 with that interval, and our second piece, negative 2x plus 3 with that interval. So first I'm going to graph the line itself. My y-intercept is negative 2, and my slope is positive 1. So I'm going to go up 1 over 1, up 1 over 1. So something that you could do is just draw dots for your line. Then look at the interval to decide where you're going to connect those points. So I'm going to connect the points when x is less than or equal to 1. So find my graph, find where x equals 1 on my graph right here. So here's where x equals 1 on my graph. So x equals 1 is where I start. Anything less than that, less than is to the left, so anything less than will be included in my function, so I can connect the dots that way. So the dots going to the right above, I'm not going to include in my function. Okay, for the second piece, I have this equation, negative 2x plus 3, so my y-intercept is at 3. 1, 2, 3, there's my y-intercept, and my slope is negative 2, so I'm going to go down 2 over 1, 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 down 2 over 1. You can see we do not have the same slope. It is not symmetrical. Okay, where do I connect the points for this piece? Well, anywhere x is greater than 1. So find where x equals 1. It does not exist there for the green equation. It does not exist at 1. So what does it mean? It can't equal 1, so I need to draw an open circle there. It can't equal 1 there, so open circle. But I'm going to continue or connect the lines where it is greater than is to the right, so then connect those lines going to the right. So be careful to watch the open and closed circles with your intervals. They don't always have to touch. Piecewise functions don't have to connect each piece, as you can see here. Example 3, analyzing the graph of a piecewise function. Enola's mother is reviewing the monthly water bills from the summer. Each monthly bill includes a graph like the one shown, which reflects the different rates charged for water based on usage. They expect to use 10,000 gallons of water next month. How much should they expect their next bill to be? So notice we're counting this, our x-axis, in thousands of gallons. So we have 4,000, 8,000, 12,000, 16,000. Okay, and you can see we have 3 different pieces on our graph, or 3 different tiers with 3 different rates that they charge. They are expecting 10,000 gallons, or 10 on our x-axis. So if we identify 10 on our x-axis, they're going to fall in tier 2. Okay, and just using our graph, we can see how much money that's going to be. $40. They can expect to pay $40 with that much usage. Okay, and remember, look at the open and closed circles. So if they spend, this looks like it's 5. If they use 5,000, they're going to be in tier 1. 5,001, anything greater than 5,000 would be included into tier 2. Tier 2 includes everything up to and including 16,000, but if they go 16,001 gallons, they're going to be in tier 3. Okay, so you don't get charged double, right? There's not one usage amount of gallons that would be in 2 different tiers. So that's why we have a closed circle and an open circle on the same input value. Try it number 3. Suppose her family doubles their usage from 10,000 to 20,000 gallons. Should they expect their bill to double? Well, they doubled their usage. They should pay double, right? Well, let's go back to our graph and look. They're going to be using 20,000, which is going to be over here. And if we just follow that graph, they're going to be in tier 3. If I look at the graph, tier 3 at 20,000, it's going to be, what value is that? It's going to be $100. Is that twice as much as 40? It's more than that, right? So they're getting charged a higher rate because they're using more water. So they should expect to pay $100 because they're now in tier 3 that has a higher rate. You can even kind of barely see it has a slightly higher, steeper slope. Tier 1 has the least rate, the less steep slope. Tier 2 is a little steeper, until tier 3 is even steeper still. So the more they use, the higher the rate per gallon. Another example to apply piecewise functions. We have wristbands that we're selling. The gym owner wants to purchase custom wristbands for a marketing promotion. She thinks she will need about 90 bands. Her assistant insists that ordering over 129 wristbands will be less expensive than just ordering 90. So let's see if we can look at this. We have 3 different rates. Okay, so we've got 3 different price points, if you will. If you go up to 50, it's $2 each plus $5 shipping. And we can write that equation, $2 per wristband, or 2x, plus that $5 fee, which is our y-intercept, or our initial value. For the next piece, 51 to 100 wristbands. Again, these are whole number intervals, right? Whole number inputs. We can't sell part of a wristband. So 51 up to and including 100 wristbands, cheaper rate, but higher shipping. So our rate is 150x, but our initial value is higher, plus 10. And then our third piece, anything greater than 100 would be even cheaper still per wristband, 1 times x, but our shipping is the highest, plus $15 shipping. So there are our 3 different equations. You can see here we've written the piecewise function. 2x plus 5, that's our first one. And here's our interval. Don't forget, you have to define the interval from 0 and including greater, less than or equal to 50. There's our first piece, or first equation. Second equation, we have 1.5x plus our fee, which is our initial value, plus 10. That is, notice it's not equal to 50 here. Okay, so you could have even said 51 here, and then we would need to say less than or equal to. That would have worked as well. But since they're including 50, they're making it less than because 50 was included in the previous piece. Up to and including 100. Okay, so equal to or less than 100. And our third piece, again, our slope is 1, our rate is 1 plus 15, and our interval, anything greater than 100. Okay, not equal to because 100 was included in the second equation. So there are our three pieces, there are our three equations, and we can graph each of those equations. So we can graph 2x plus 5, and then erase the pieces that do not exist in that interval. So on the next page, we're going to see the graph. So here's the first piece, 2x plus 5, okay? So it intersected the y-axis at 5, and the slope was 2, so up 2 over 2, okay? Or up 10 over 5, or up 20 over 10. Looks like how they did it, okay? And you can see it would continue on, but that only goes up to 50, which is right here. So including 50, closed circle, but everything else is not included. Should be blue. Everything else on that graph is not included. So we would not include that or just erase it. Okay, and a closed circle at 50. For the second piece, we start at 50 but don't include it. So that's why we have that open circle. And the rate now is 1.5. Okay, so then we did our slope. And that goes all the way up to 100, including 100, so a closed circle at 100. When you're graphing, you can just graph, and go back to this page, you can graph the points at the end of the intervals. So you can do one point at 50 and the other point at 100. And those are your endpoints. And then just connect those 2 points using your slope. So what I would do if I'm graphing, I would start at 50, and then go do my slope 1.5 up and then over 1. That's what I would do. You could also see if I extended this yellow line at 10, it should intercept at 10, halfway through. Okay, and the third piece is this green line, and you can see I'm trying to do it as best I can. If we extended it through, if you're just drawing the whole equation, so y-intercept starting at 15, and then using the slope, it's a little bit better, using the slope, or you can just use the endpoints of your interval. So the interval started at 100 but did not equal to 100, so we have an open circle there, and then from there we go up 1 over 1. From there we go up 1 over 1, up 1 over 1 to use our slope to make the other points. And again, it continues on. We only connect the points going to the right, greater than. So I tried to highlight where you could see the line extended through, and then how we do the circles, closed circle or open circle, to define our intervals, and then connect the points only where that graph exists in those intervals. You can see that they don't overlap. Those pieces don't touch each other. Okay, and it does fit the description. It has a higher rate per wristband, $2. It should have a steeper slope. The next piece, $1.50 per wristband, has a slightly less steep slope. And then if you buy over 100, even cheaper, $1 per wristband, so even a slightly less steep slope for the third piece. Let's go back to the question. She wants to buy 90. Is it cheaper to buy more than 129? So those are our two numbers we're going to evaluate, but we need to look at which piece or which equation we're going to use. So if she's going to do 90, that's less than 100, but more than 50. So that fits the second equation. So we're going to evaluate 90 using the second equation, 1.5 times our input plus 10. Okay, so it tells us which interval or which equation to use. So if they only buy 90, it would cost $145. 129, that is greater than 100. So that means we're going to use the second equation or the third equation, And so plug that into the third equation. 1 times the input plus 15, higher shipping rates for more wristbands. And then it would be 144. So yes, it's actually $1 cheaper to just buy more, and then you'll have a lot extra that you won't have to make another order. Number 4. What is the difference in cost between one order of 200 wristbands, 2 orders of 100 wristbands, and 4 orders of 50 wristbands each? Okay, so one order of 200 wristbands. 200 is greater than 100, so we're going to use the first equation. So f of 200, sorry, the third equation. We're going to use the equation where it's 1x plus 15. And if we evaluate it, that would be 200 plus 15. So if they order 200, it would be $215. 2 orders of 100 wristbands each. So 100 wristbands is the second equation. So we're going to do f of 100 using the second equation, 1.5 times x plus 10. That's our equation. So we're going to evaluate, plug in 100. Our input is 100. Okay. So we would get 160, but how many orders did they have? They had 2 orders. So that total would be 320. And the last order, 50 wristbands each. So if I'm evaluating 50, that's the first equation. Okay. And so that would be 2 times the input plus 5. So 2 times 50 plus 5 is going to be 105. But they ordered 4 of those orders. So multiply that number by 4, and we would get 420. Is it better to order 200 or to break it up and do 200, 2 orders of 100, and then 4 orders of 50? Okay, so if we just buy them all in one, we get $215, right? But if we do 2 orders of 200, we still get our 200 wristbands, but now it's going to cost $320. It's going to cost even more. And if we broke it up into like orders of 50, smaller orders, we still need a total of 200. It's even more expensive. Okay. So the difference between ordering it all at once or ordering it in each of these pieces. So the difference between these two is going to be $105. And the difference between 4 separate smaller orders and the 1 big order, that's going to be a difference of $205. So better to buy in bulk. We made it to the concept summary for piecewise defined functions. Remember, we use this notation, we use the brackets, and then you'll have your equation for the linear equation, the graph, but always include the interval. So it will fit this line only when it's less than or equal to 3. Then the second equation is a separate line, and that line will exist only when the input is greater than 3. And we can graph each of those. So you can see here's my negative slope equation, and if we graphed it, there's the y-intercept at 2, negative 2, and the slope is down 1 over 3. You can see, okay, and we keep doing that, down 1 over 3, okay. But it does not exist here. Anything greater than 3 does not exist in that function. And it's a closed circle here because it can equal 3 for that first equation. For the second equation, the y-intercept is at positive 1. So that means it would go through positive 1. And then up 1 over 1, up 1 over 1, up 1 over 1. So we would have that graph. But looking at our interval, it only fits this blue line when it's greater than 3, so it does not equal 3. That's why we have an open circle, and then it continues. We connect the lines going to the right. So none of this would be included in our function. That's Piecewise Functions. Make sure to leave your questions in the comments, like and subscribe, and come back for lesson 3.